I am starting recording, and welcome everybody back. Happy Garbage Day, our last Garbage Day together. Zoomers, I don't know if you can see, I've got my merch on today. I have a t-shirt that Jonathan got me that says Happy Garbage Day and lisahoffman.com on the back. It's one of a kind. So the channel is not selling merch just yet, but I have one. So, would you like to find out how your extra credit opportunities are going? Drum roll, please. 15 out of 29.
So beating the other classes.
You're beating the other class, so good work on that, I think. Actually, no, they're beating you because it's two sections. I have an online section and a separate section this time, so yeah, they're beating you guys. You can't let that happen. This is the intermediate class. So it's the only class that I teach that has a requirement to it. Pump those numbers like it's a meme coin, folks. I'm also going to smile and nod at that. I have no idea what that means. Would you like to clarify? Educate us on today's slang?
So within certain cryptocurrency blockchains, Solana being the primary one, you have things called meme coins, which generally are just pump and dump schemes, not unlike certain penny stocks.
Thank you for clarifying. I'm not even going to pretend I understood that either. There's a few words in there I've recognized, but otherwise I don't understand how I fit together.
Fair enough.
Thank you for attempting to educate me, though. I appreciate that. I'm still trying to figure out what the hell skibbity means. My son has started saying this. I'm like, are you sure you're using that correctly? Like, I don't know. But yes, 15 out of 29. And I checked the distribution of the Qualtrics survey. It looks like it went out to folks. So if you need another link to that, please let me know. I can resend the link. Otherwise, that's your other extra credit opportunity. So each person who does the Qualtrics survey gets 1 point. If at least 26 of you do the classroom survey from the university, then you also get 1 point. And yes, so any questions on that? This survey closes Saturday, by the way, so you've got a few more days to get things in, and so nag your friends. There's a little friendly peer pressure to get things to move in here. All right, so I don't know how many folks heard this before, so I'll repeat myself. I posted a new version of example 7b that has some typos fixed, and the equations had some inconsistencies, so I posted that this morning. I also updated the Excel sheet that has the figures in it because I added one more, and so I wanted to show that to you all as well. So my plan for today is just to kind of wrap up what we have with respect to the remaining slides in lecture 7b, example 7b, and then next time we'll focus on some story problems, 2 from the formative assessment, and then I have 2 more in mind if time permits, and we'll do some bigger picture talking at that point. So how's that sound? Good? Hanging in there? All right, anything I'm forgetting or that you want to ask questions about before we dive back in? Okay. So we were talking last time about random quadratic time models, and I did not feel like that was my best work. I'll just put it out there. I felt like I sort of got a little bit, I don't even know what the right word is. Can I blame this point in the semester for it? Can I just say I just had an off day? So I'd like to try to redeem myself and suck less this time. Is that okay? We're good with that? Suck less. High goals. High goals. Yes, okay. Because your last homework has random quadratic or quadratic models. It's actually fixed quadratic random linear. So this will be relevant in terms of how to talk about the fixed effects. So start at the beginning again. This review, that work for folks? The beginning of this section, I should say, Model 2A. I'm on page 20, still of 39 here. So baseline model has no time invariant predictors. We do that so we can see how much variance we have of each kind to begin with, and then we can watch each kind have its variance explained by time invariant predictors. So in terms of predicting slopes for things that would be model implied, there's only one that would be relevant. So one thing that I did in these equations, I used to have the 2 out here because it's twice the quadratic, but in terms of how you would actually implement that in the software, you would have to multiply time times 2 instead because you can't change the fixed effects as they are estimated. So I rewrote the equations in here to be consistent to display that idea. And as a reminder, the quadratic slope needs to be multiplied by 2 because it is half the rate of acceleration of the function. So to talk about how the linear slope changes over time, we would multiply time times 2 and then use the quadratic to talk about that. So twice the quadratic is how the linear time slope changes per unit time. All right, so we have a function where if I did it with the hand gestures, starts out, I'm getting it right this time, goes down and then kind of levels off, right? Does that look like it's correct to y'all? Yay, finally, I can do mirror imaging. So I would say the linear slope is becoming less negative over time by twice the quadratic. The one that's provided here is specific to what as a review? Can I say this is the linear slope is minus 120 the end? Or does my sentence need work? At time 0. So yes, there will be homework questions about this because this is conditional at time 0, which means you need to know where that is in order to interpret it. And it's not describing the change from 0 to 1, by the way. It is literally at time 0. Like it's the line that is, the slope of the line that is tangent to the curve at that point. 10, can I get a physics ruling on that? Did I say that correctly? The slope of the line that is tangent to the curve at that point?
Yeah.
See, sucking less already. Hashtag goals. All right. So one thing I wanted to point out here, you'll see this across all the models. Look how correlated the two slopes are. They're almost perfectly correlated. So this will cause error messages to show up in your output if this thing goes to -1. And that is somewhat unavoidable because time and time squared are related to each other. If you were concerned about it causing model convergence problems or something like that, though, you can mean center time, and that would render these two random effects as uncorrelated as they can possibly be. But they're still going to be correlated to some extent. In terms of effect size, so far, linear and quadratic slopes have explained about 3.7% of the overall variance in response time. I'm not doing any pseudo R-squares with this model. What I would have already done is compute pseudo R-square for the residual based on these two things, and I did that in example 6a, I believe. But we are saving the values. So Stata folks, do you need me to go over any of this stuff that's happening right here? Saving the values and using them and stuff, we're good with that? Okay, cool, just let me know. I did compute some reliabilities here. I don't think I asked you to do that in homework, but just for your edification. Here's the same thing in R. So using the inhibitor function, thank you, Vladimir, for defining that for us a few weeks back, to create time squared. And let's see, yep, effect sizes. R, folks, do you need any further treatment of this, the idea of saving these things? Are we good with that? So the key to understanding these numbers is this piece of output right here. What that's doing is printing a table of variance components and changing it into a data frame so that we can refer to rows and columns. So for instance, the first one is row 1, column 4, and it's all column 4 because in this table, those are the variances for each of the things. So you just have to figure out which row you're in. The order is variances, then covariances, then residual. So it just depends on the size of your model, how many rows you end up with. All right. So are we ready to talk about age as a time invariant predictor and do it better this time? We're good? Good enough anyway? All right. So this time, I have age centered at 80. I picked 80 because it was near the mean of the variable. Once again, these are older adults. Because I have 3 different kinds of individual differences, random intercept, random linear, random quadratic, I have 3 potential roles that age can play. It can explain why people start out faster or slower, why they initially improve more quickly or less quickly, and then why their performance sort of asymptotes off more or less than other people. So 3 different aspects of change contributing to the curve here, individual differences in each. So the fixed effect predicted outcome, removing all of the variance related terms would be this right here. So these are the ingredients that I would need to figure out how to compute simple slopes or conditional slopes on each value of the moderator. So that then, to review, let me see if I can move this over here. Does it go over? Almost, not quite. Well, I'll move it over temporarily. How's that? There. So step one in trying to figure out a simple slope is to gather all of the terms that have that slope in it. So for instance, if I want to do the linear slope of time, then in here I need this, I need gamma 1O, I need gamma 2O because time is part of that. I do not need the main effect of age. I do need these two interaction terms. And so then everywhere that I'm talking about the quadratic time slope, I need to multiply the time value I put in here by 2. So I have extracted out the t part. T is an abbreviation for time since these equations are getting a little long. And then what's left is just built from the ingredients that had time with respect to the fixed effects here. So down below, I've computed predicted linear slopes at particular occasions, but then for particular ages as well. So you can condition on both of these things at the same time. Okay, does that make sense? Good with that much? Okay. Then quadratic time slope. Same idea. I go into the equation here and find everything that has time squared. Extract those pieces. So this one is a little bit more straightforward. The quadratic time slope is unconditional with respect to time. So the way that the slope slows down is a constant change. It is conditional, though, on age, because then your quadratic can vary based on how old you are. The one that is given by the model is specific to age 80, because that's when this part would drop out, but we can figure out what it would be for any other age. So these are the terms that I would use if I want to talk about how age is moderating the growth curve, or in this case, the decline curve, as it were. If I wanted to talk about how the effect of age changes during the study, then these two would be relevant instead. And so I'm going in, finding everything that has age in it. So I need the main effect of age, and then I need how it interacts with time and how it interacts with time squared. And the main effect of age is conditional on time 0, because that's the point at which these two terms would drop out. Then last but not least, I have, and I kid you not, this is what people say, a simple two-way interaction. Not simple at all, but simple in the sense of conditional, because we also have age by time squared as a three-way interaction. So that means how age changes the linear slope changes over time. So to figure that out, then I have the simple, so to speak, age by time interaction, and then I add in twice the value of time for which I would want that function to continue. And by the way, it took me a lot of work to make sure this math was right, because deriving things and figuring stuff out like this is not my strong suit. But do you know how I did it? This is a pro tip for those of you in life. Get one nod. Do you want to know how I did it? Wouldn't it be nice to know that you're not screwing things up for your future self? Yeah, Vladimir, you nodded first. How do you think I did it?
Changing the reference values in the model.
Changing the reference values, and I'm laughing because Alex says, ask Jonathan. Close second. That is how I get my R code to work. Sometimes I need his help with math, but in this case I did not, because yes, that is what I did. So I recentered time at a different occasion, and I recentered age at a different place, and then I made sure that all of the linear combinations that I had matched the corresponding output in the recentered model. And indeed, that is how I learned to do this a long time ago. Like, that was how I was taught to get simple slopes out of interaction terms, is to recenter and respecify. It works, but it is probably more work and more confusion than is necessary. Occasionally, I will still do that for something where I'm just too lazy and I need something quick. So for instance, I'll give you a hint, an example of this. In your homework, you have two groups. You have a control group and a treatment group improving well-being, right? So control group is the reference. That means that everything in the model is specific to the control group for the most part. If you wanted to get things for the treatment group, you can write these kinds of statements, or you can just change the treatment group to the reference and rerun the model, and then everything's for treatment. So that is probably less work, I think, to run one more model to get everything than to write out all the statements. But I did want you to have the documentation that goes with these ideas. The unofficial co-instructor of 6271, Jonathan. Yeah, that's true. But if you're going to do that, he's the unofficial co-instructor of most of my classes, let's be real. And sometimes, very occasionally, I make an appearance in his. Very occasionally. This is what happens. So yes, I was able to verify that this stuff is right by rearranging the model and then making sure the parameters came out the way I had thought that they should. Okay. So then, we're adding in age. The code itself is pretty straightforward. Here's the stated version of it. Now let's go through, let's look at, I keep looking at the stated version. Let's do the R version, and I'll come back to all this stuff here. Keep going. Do I have that? Where'd it go? Oh, I didn't print the R version. My bad. We're going to do the stated version. It's okay. All right, here we go. Zoom in way in so we can see the numbers better. So 1950. That is my predicted response time. When and for whom?
Time 0.
Time 0.
For an 80-year-old.
For an 80-year-old. And this, by the way, is why I name my predictors with the centering constant, so then I don't have to remember. I can just read the output. Okay, this right here, this is my reference growth curve. So it has the same shape as before, initially declining steeply, and then the amount of decline is kind of leveling off, would eventually predict to come back up the other side. And by how much is the linear slope slowing down per session? And don't say 13 or 14. By how much is the linear slope slowing down? What's the trick? Multiplied by 2. Yes, so the linear slope is becoming less negative by about 28 milliseconds per session. And these values are specific to an 80-year-old, given the interaction terms, because they're being moderated by age. Yes, 2 times 14. Very good. All right. Now, how does age affect the growth curve? That's the question we got to figure out. And it does 3 different things. So the main effect, what does this do? Words or gestures, take your pick.
Older people improve less. No. Older people improve. Yeah.
Older people, start there, but which term is this modifying?
The linear time.
Not yet.
Oh,
This is
no.
age by itself.
Oh, on the intercept.
This is the intercept,
Okay.
yes, so this is this idea. Yes, in this study, age is time invariant. And so I have time as how many sessions of practice they have, and age is how old they were when they started the study. So older people, for every year older they are, they start out about 29 milliseconds slower at session 1, which is our time 0. Okay, so not unexpected right there. Now the next one, what does age do to the linear time slope?
Older people improve more.
Yeah, this is a more negative, so that means people who are older improve more. For every year older they are, the linear slope at time 0 becomes more negative by 5.6. So for every year, this is how the linear slope changes at time 0. Okay, with me so far? All right, then we got the quadratic. What does age do to that? Zoomers, I'm watching the chat. You can play or you can gesture. This will be a hard one to gesture, but I think you could do it. Need my arm to be like more bendy. I got the bones in the way. What does age do to the quadratic time slope?
Can I ask a question about the other one first?
Yeah, please do.
The first interaction between time and age.
Yep.
So
That one.
at what time is that at time 0 to 2, or is that okay?
It is at time 0 because of the three-way interaction.
Okay.
So this two-way is conditional on the third variable being 0. So this would have to be time 0 for this term to drop out.
Okay. Okay. Gotcha.
yeah.
Thank you.
So I'll say that a little differently. Age moderates the linear slope at time 0, like only by this term, because that is the point at which this one would drop out. Age modifies the linear slope by this much specific to time 0. It's going to change as the study goes on. Did that help? Okay, and my other question, what is age doing to the quadratic slope? Your choices are more positive, less positive, more negative, or less negative.
More positive.
This is a more positive, so it's making it stronger. More positive, yes indeed. And this is the point at which your reader's like, so they start out higher, but then they change more, but then they're more bent. Can I have a picture, please?
More positive quadratic is more bendy.
More bendy, yeah. Bendier. I think both of those are correct.
Quadratic
Bendier.
will go down and then come up. But
Yep.
it's just
Here's the picture I made this morning. So let me show you how I made it, and then we can talk about it. And this is a way that anyone can make pictures that is software agnostic. So rather than make the same pictures 3 different times, I decided to do it this way. So I threw in all of the coefficients over here, and then just pasted them down all the rows of predicted values that I'm going to have. So these came directly from the output. C1 sesh, oh, that's an old one. This is what I used to call this variable like a million years ago. We'll call that time. I have times 0 through 5, so that's creating a growth curve for one kind of person. And then age 80, I have plus or minus 6, because that's roughly 1 standard deviation. So I'm making plots for a predicted 74-year-old, 80-year-old, and 86-year-old. So here is my 74-year-old, here is my 80-year-old, and here is my 86-year-old. Then the predicted function, I will double click on it so you can see it pop out a little bit, but it's the intercept plus slope times variable plus slope times variable plus slope times variable. So only the fixed effects are relevant in here. Note that any terms that have to do with quadratic time, I've explicitly put in time squared so that you can have that. I think in Excel it is a caret maybe for squared. That sounds right. Like, is that right? Yep. Okay. In SAS it's 2 stars, and in Plus it's like 2 stars. It's a caret in Excel. I forget which it is. So I sometimes just write it out like that. Then, because I wanted Excel to understand that these fit together and that these fit together, I transposed them. So I said, okay, grab that one and then drag that over. So now I have an x-axis made right here, and then I have 3 rows for the moderator. And this is pretty universally what a picture to show moderation of a growth curve would look like. You would have the growth curve time on the x-axis, and then you would have different lines for different values of the moderator. So then the pattern, the highest line here is for an 86-year-old. The next one down is 80, and then the last one is 74. So the main effective age is illustrated by this difference between lines right here. The older people are slower at the beginning. The older people also have a steeper slope at the beginning. So if you drew a line right here at that first triangle, you can tell that the trajectory right here is steeper. But then the older people also have a bendier pattern here. So this is the stronger negative linear paired with more positive quadratic pattern that's being created here. So it looks like they do less well at the beginning, they improve more rapidly initially, but then they level off more. Which all makes sense because you can't continue improving at the same pace forever. You run out of, you hit some sort of optimal level of performance. And these curves, by the way, are not predicted to stop. What are they predicted to do under this model? Yeah, come right back up. Oh, this way, the other side. Getting it. Yep. So some folks do not like this model for that reason. An alternative that would look more asymptotic would be to use log transform time, but I decided not to do that to you because then interpreting the slopes becomes exponentially harder, and that's no pun intended, but it kind of is. Ba-doom. Thank you, folks. I'm here all week. Not next week. I'm just living in my basement next week. All right, so questions on that model and what it's doing. Okay, in terms of effect size, let me zoom over to the p-value column here to help make this point. So it looks like the main effective age is significantly positive, but the two interactions are actually not significant. So we probably could get rid of those if you wanted to. I did not choose to because I want to control for age with respect to all three terms and then not have anyone yell at me about that. Here's a hypothesis test for all the age slopes together, if you wanted to have one of those. And then we get into the simple slopes. So here's the equation from the first page with this model. And I wrote that in here so you can see the logic as it's implemented within Stata code at least. So c dot time is that one right here. The c time squared is gamma 2O, and then I have twice the value of time that I'm predicting. So this would be for, I have sessions 1, 3, and 5, which would be times 0, 2, and 4. Yep, got it. And then I have time times age, and then I'm filling in the value of age that I want, and then time times age, in which case I'm multiplying the terms together. So I end up with minus 24, for instance, minus 48, and so on. The code right here does all of that for you, by the way, but I was just writing out longhand what is happening within these statements here. So if you need to get the predicted slope, like for this age at the end of the study, like these are your breadcrumbs. So in this instance, it's 2 times time for all the quadratic terms that are in here because we're predicting linear slopes. And so then you can see the range here. For this age, the slope is slowing down, but it is slowing down more for the older folks relative to the younger folks. Quadratic time slopes, I can get how age modifies those, and so I have quadratics for each age as well. And you can see the pattern that the quadratic is becoming stronger, so the line is getting bendier. Then we have age slopes. So the other way to think about this function, rather than focusing on how the slope of the lines differs across groups here, across ages, we can talk about how the distance between the lines is changing over time. So folks are more spread out at the beginning, they become closer together as the study goes on. But the way in which they become closer together is not linear, it's quadratic. So that's what I'm trying to illustrate here. The age slope at the beginning is for session 1, time 0, and then we can add age by time, and then age by time squared. And for these, it is time squared, not time times 2. Here's your carrot. Because we're not estimating linear time slopes, so we don't have to multiply things by 2. We're estimating age slopes. So then I'm just filling in the values of time and time squared in these statements. The results then show the pattern a little more clearly. The effective age diminishes at first by quite a bit, but then the rate of diminishment slows down. So age matters less as time goes on, but even less. At some point in the future, age would stop mattering. So you can see the p-values here are creeping closer to 0.05. And then last but not least, how age changes the time slope varies by time, linearly. So to do that, since we're talking about the time slope being part of the story again, it's 2 times time. I forgot that right here. There we go. Looks like I get to repost the handout again. Eventually, I will trap all the errors. There we go. So then this is the age by time interaction down here. Nope, lost it. There we go. So this is how that changes over time. How age affects the linear slope changes over time. All right, effect sizes then. We're up to about 11% of the variance in response time. The contribution from age to that was a 0.07. Then we get all the corresponding R code in here. So our folks, I did the same thing. We have the equation, and then I have the contest 1D statement. The unfortunately less transparent version of it because it's not tied to the parameters, but they're in the order in which they show up in the output. All right, our folks, do you want to go over any of these? Or a question?
By
Yes.
output, do you mean a data frame? Like we made a data frame and then that's following the order of our columns?
The output from the Elmer call. So the table of fixed effects, it is in the zeros and ones go in that order as multipliers. Yep. Okay. So it's the same logic as in the stated code, just putting it in the spot that goes with a fixed effect rather than explicating it specifically. All right. Any questions on these statements, contest 1D? I know they're annoying, but I have not found a better way that is universally applicable. Okay. Then, pseudo R-squares. So in your homework, I asked for effect sizes, and I don't tell you which one to look at, because that's part of what you're supposed to figure out. But there's only three kinds, so process of elimination will work. But which term is responsible for explaining 10% of the intercept variance? Age, age by time, or age by time squared?
Can you repeat the question?
Yep. 10% of the random intercept variance has been explained now. Which term did it? Age, age by time, or age by time squared? I'm hearing something, but can you speak up? Or type? No. Which one did it? Age, age by time, or age by time squared? Age, yep, age by intercept. Main effects adjust intercepts. That means they predict intercept variance. 3% of the linear time slope variance was explained. Which one did it? Age by time. Yes, exactly. And very little of the quadratic slope variance was explained. Which one did it? Age by time squared, yeah. Now what if this wasn't here? Like in your homework, you don't have one of these. Then what is age by time squared going to explain if you don't have random quadratic time slope variance? Residual. Yeah, it has to come out of here in that case. So if you do not have a random slope variance that goes with the level 1 predictor that's in your interaction, it has to explain residual variance instead, and it gets a new term, new vocabulary from last time. Remember what we call it?
Systematically varying?
Systematically varying or non-randomly varying is a synonym I've seen as well. Yep. And I have had to argue with reviewers about this, by the way, that whether or not those are acceptable. So if you have a systematically varying effect, be prepared to defend it. They discuss this in the Snyders and Vosker multi-level book, in the Radenbush and Bright book, and I talk about it in chapter 7 of my book as well. So you can cite, at least cite those sources as people saying this is a reasonable thing to do so long as you don't have a random quadratic slope variance that you're mistakenly omitting.
So in that case, if that happens, will we see a negative pseudo-aspiracy, or how can we tell?
So whatever, basically this contribution would show up as reducing the residual, not by the same amount because they're different sizes, but that's where it would go. Yeah. Okay, other questions? All right, let's add reasoning because I want to make a point. This is a new point. So I am only adding reasoning as a main effect on the intercept has an interaction with linear time and has an interaction with quadratic time. We're not doing age by reasoning in this model. That's just nonsense. I can't do a four-way interaction. I can, but I don't want to. Let's put it that way. Is that fair? I'm sure a lot of you have similar, like, yeah, I could do that, but no. No thanks. Bet. That's what the kids say. So then the story of simple slopes gets longer, but not necessarily more complicated. There's just more terms that would contribute to each. So I've got all this stuff in here for the Stata folks, and then I have the corresponding R output. We'll look at that here. So in this case, this is annoying to me. R insisted that I put the terms in this order. So rather than adding the 3 new ones at the end that I would want, it's like, nope, you have to do it this way. So there they are. If someone has stronger reasoning, what happens to their intercept?
They get better faster.
What happens to, well, they're not getting
Oh,
better.
sorry.
Yeah.
They start out faster.
Yeah, they start out. Yes, so people who are stronger in reasoning are faster at baseline. For every unit better in reasoning they are, their baseline response time is lower by 27 milliseconds. What happens to their linear slopes at time 0? More negative, yeah, stronger. So even though they're doing better initially, they're still improving more initially at that rate. And what is happening to their quadratics?
More bendy.
More bendier, yeah, more positive quadratics. So I have that picture in here. So similar shape, except the order of the lines is different. Now the folks at the top are the less able folks, and the smarter folks are at the bottom here. So the smarter folks are lower, but they change more quickly initially, a little bit, and then they have a bendier line. In terms of significance values, though, so it looks like we would want to keep the main effective reasoning on the intercept. That is significant, and age remains significant, even though the effect has been a little bit reduced, as you might expect, because these two are correlated. For time by reasoning, do you think we need that?
Is reasoning measured only once in this study?
Yes.
Then no.
Then no. What about time by reasoning squared?
Same.
Doesn't look like we need it, right? Should I dump them both?
If you want to control for the impact of reasoning, you should leave them.
If I wanted to control for reasoning as like a special privileged variable, I would leave them, but reasoning is not privileged to me.
Okay.
So I think we can agree that we should dump the highest order interaction that's not significant. We'll check the effect size too, but it's not going to be a big thing. What about this one?
Also not
Dump it or keep it?
I mean, it's not significant, right?
It's not significant.
So dump it?
So we got one vote for dump it. Can we test if we need it? Yeah, this is going to be an empirical question.
Oh.
Yeah, because yeah, I'd look at this and be like, yeah, we don't need either of these. Let's just dump them. Let's find out. The 3 slopes lumped together are significant, but it's probably just the main effect that's doing the lion's share of the work. I now have simple slopes for various values of reasoning and time, holding age constant. So we can talk about those. Quadratic time, same thing. Reasoning slope changes in the same way that age does, so the same ideas as before. We have picked up another 5% of the variance in response time with reasoning. And each of the terms then, I can talk about pseudo R square for the model and then the change for that. So it looks like the main effective reasoning has picked up another 4% of the intercept variance. The what has done this damage? What's responsible for that? This is the time slope line. Reasoning by time. And by the way, if you compute a pseudo R square in your homework and it's negative, keep the negative sign. These are signed values. So what happened is The first model had explained 0293, and then the second model had explained 0237. So it actually went, the change is negative. The R square went down instead of up. And then reasoning by time squared explained about 2% of the variance. So 2% is not particularly exciting. Now, let's see what happens. Now note my equation here. This is not something that I see very commonly, but I do it because spacing is your friend. I like spacing things over to show that there's a hole here, that something is missing, because it makes it more obvious when you present it in a grid. So I don't have a gamma 2,2 anymore.
So it's systematically varying? No, it's not.
So the quadratic slope is still random in this model, but it is a function only of age and not of reasoning.
Okay.
So previously, reasoning by time was not significant, reasoning by time squared was not significant, so we removed the highest order term. Now let's see what happens. Ding, ding, ding. Different result. The p-value was like 0.46 before, now it's 0.22. So the answer then would be test it, don't dump them both.
So why did it change?
Why the change? That was going to be my next question. Hang on here, I want to split screen so we can compare. So let me go find the results from the previous model, one moment. Scrolly, scrolly, scrolly. Okay, almost. I can fit them on the page. All right, so time by reasoning before was negative 3.6, and the p-value was 0.43. Time by reasoning now is not only significant, it has changed sign. It's 2.93, and previously it was negative 3.6. So why did this happen? I will also note the standard error was 4.5, and it is now 1.2. Any guesses? Why this may have happened? I can think of two reasons. Two things that make this different. Let me go with the easier one first. What happens when predictors are really correlated in regression models? It's like called something. Starts with a C, sometimes starts with an M, sometimes has one L, sometimes has two L's.
Multicollinearity?
Yeah. Collinearity or multicollinearity. So do you think that time and time squared might have some collinearity? Probably. So in terms of being able to isolate the unique effect of reasoning by time relative to reasoning by time squared, that's going to be a little tricky. So that is evidenced, I think, by the difference in the standard errors. There is a lot more unique variance available for this interaction term when it is not paired with the quadratic version of it than when it is. So that's one thing. So that could explain the difference in significance. If you cut the standard error a third, then you have a lot less error to test the slope against. But what would explain the change in sign?
Is that because, like, the slope of the time squared was bendy and it was somehow, like, messing it up or making it harder to figure out what it was or something?
It is related to the bendy, but I would not say it's messing it up. But definitely right track. When is this the reasoning by time interaction?
At time 0?
At time 0. When is it down here?
It's a constant.
All the time. So in the model that has quadratic time by reasoning is conditional on time 0. It is how reasoning affects the linear time slope at the beginning specifically. Down here, without that interaction, this is how reasoning affects the time slope all the time. So they don't mean the same thing. And I have, let's see, let me find the results for that. For the reasoning slope, nope, time by reasoning. Here it is, reasoning by time. This is the one I wanted. So in the model that has reasoning by quadratic time, the reasoning by linear time slope is conditional at session 1. So that was the value that we saw here. But you can see what happens to it according to reasoning by quadratic. It becomes less negative and then eventually flips over into positive. So you can think of the 2.94 down here as kind of like an average of these. It's marginalizing over each of these sessions. So, long story short, in these models, when you have nested effects like this, like time by reasoning is nested within reasoning by time squared, I would not dump them both at the same time.
So are quadratic models usually most accurate more like in the center of your equations because they do this so fast that they're often just wrong at the beginning and the end?
I would not say, so the question was, are they more accurate in the middle? And the answer is yes. I would not say wrong, though. Basically, if you have a curve, like the middle of the curve is going to be the most well-estimated spot. And so as you move out, then things get a little bit more wiggly.
So they're impacted by outliers more at the...
I wouldn't say outliers, it's like a physics thing. Hang on, I got a prop. I don't have a bendy prop, but I have a regular prop. Okay. Fulcrum. Yeah, I have a telescoping thing. It's a pointer stick. Highly recommend you get one of these. It makes you feel very professorial to point at things. Or to go like stab your students who've fallen asleep. But if I have just a linear slope, right, like flat slope, and if I change the slope, like the middle doesn't change very much, but the ends change a whole lot. So the ends are less well estimated because they're sort of they're more dependent on what the slope is. So you can see that in standard errors too for things, like they tend to be smallest in the middle and then they increase as you move out.
And confidence intervals.
And confidence intervals do the same thing. And that is true for like predicted outcomes. They have the smallest standard error at the mean of the predictors, and they increase as you move out. The ends are more uncertain. Yep. So let me unsplit this for a second. So point of the story, because linear and quadratic time are so correlated, I would be careful dumping things for both of them in the same shot. I would want to make sure that after you remove anything related to the quadratic, that reevaluate the contribution of the moderator to the linear term, because it means something different and it may be better estimated without it.
That's a question.
Yeah.
So when you're analyzing similar model like this, to recommend just throwing all at once and then removing them, or adding them one by one?
Okay. I love that question because it's a beautiful segue to the few slides that we haven't talked about yet. So give me like 2 minutes and I'll answer it. That works? Because I'm kind of tired of looking at code. Anyone else? Like, yeah, no. So here's the revised model that shows the same tendencies, except now everyone's bendy is constrained to be the same. So there are differences in the intercept and differences in the linear slope, but those differences stay constant as time goes on. All right, lots of code, lots of code, lots of code. Same things here. Effect sizes, more code, more code, more code. Here's education group. By the way, I fixed this equation. It used to say high versus. That was because in SAS, the last reference category is the default, so I had written it from that perspective. That is no longer the case, and so I made everything consistent to start with low as the reference category. All the same results as for the other models. Education doesn't matter, but here's an example using IDOT and Stata to do categorical predictors, as well as in R using, what is it called, factor. Yeah, putting education group as a factor variable. All right, and then that's it. I'm out. So here's some words, as usual. 39 pages later. Okay. Now, strategy time. Slide 38 of lecture 7B here. So here's my preferred strategy. If you have an interest in multiple different predictors of a growth model, I like to find out what each is going to do all by itself first. So I would have a model with just age, a model with just reasoning, a model with just this, and then look at the patterns. To me, it's sort of like a tournament. Like things that don't matter when they're all by themselves are unlikely to matter in conjunction with other things. Like you can have suppression effects for predictors that are negatively correlated, but I don't see that very commonly. So then you can think about like what is the effect of age, for instance, and then what is the effect of age after controlling for this and that and the other thing. So hierarchical models can be more difficult to defend because someone is going to question your order of entry. Like, why did you put age first? You should have put reasoning first. Like, and they're kind of right. Like, how do you defend that? So I've seen folks do it in layers that correspond to designations of control versus substantive. Like, that's a strategy, is like dump everything in that you don't care about that reviewer 3 does, and then dump in the stuff you care about and talk about it. But things will change as you add stuff to the model. By the way, there is an easy way in code to do this more efficiently. And I do this when I'm cranking analyses for people. You can hack the concept of stacked data. So let's say that I have 10 different time invariant predictors that I want to analyze. That's 10 models, right? If I'm following my own advice here, what if I could do it in one model with a by statement? Yes. So what you can do is stack your data to make a new column called like predictor, and the first time through it's age, and the second time through it's reasoning, and the third time through it's whatever until you get all 10. Add another column that is like a string for which predictor it is, or a numeric index of some kind. And then you can run one model by predictor, and it will spit that model out for all 10 different versions. And if you have, say, 10 outcomes, and you want to look at 10 predictors, that's 100 models, right? You do the stacking trick one more time and it's still 1. At least in SAS, the labels that you do the by with get saved to the data sets that come out of it. So then you have one giant table of fixed effects that are labeled by which predictor and which outcome it is. And then you can filter and sort and do all kinds of stuff to process that more readily. Vladimir, I'm sure there's a way to do this in R, right? How do you tell it to run the same model for different groups?
Personally, I have my own helper functions. So what I do is using the formula statement in R, you can define, for example, a set of covariates. So then in a for loop, you can just pass a vector with the name of the predictors you are interested in. So you are saving each model with the results in a list in R. And then you have the full set of results for your predictors and the set of covariates in one file.
Very cool. Yeah, I knew there had to wait.
Helper
And-
functions.
Helper functions. Okay, and then 10, is it by sort or something like that in Stata? I've seen this before.
Believe you. My strategy seems more similar to Vladimir's, where I'm running loops, and then I use some of the Stata helper functions to create Excel spreadsheets and whatnot. Although you've introduced me to frames, and so those have been much more powerful than what I've used before.
I don't know how to use frames. That was someone else who did that.
Okay, well, I think they're really cool, and they're going to be my new thing. So.
Okay, so yes, once you get to the point where this work is annoying and it's labor intensive, there are ways to make your work less annoying and labor intensive and all the different packages. So if you have like, that would be like for the first pass, is like to see what's significant and then combine things together. So you can then combine them in ways that make sense, but be aware that you'll have to address potential criticisms about the order of operations there. And you may not end up at the same place. Like if you add something in, take out what's non-significant, add something else, take out what's non-significant, and someone else goes about it in a different order, you may end up with a different final model. That's just reality, and there's really not a good way around that per se. In terms of model complexity, I recommend multivariate walled tests in certain situations in which you are not necessarily wanting to keep all the terms. So for instance, let's say that I have education by time squared at a p-value of 0.04. Well, that's like marginally significant, and if I keep this, that means I have to keep education by time and education on the intercept. Like, is it worth having all three things in there? That's an example of when you would want to lump together those three slopes and get one F-test for it, or a chi-square test if you're working in models that don't have denominator degrees of freedom. Keep in mind that if you're using REML, which we have the entire semester, you cannot compare -2 log likelihood, AIC, or BIC when your models have different fixed effects. They're not on the same scale. And that is the reason why in my first edition of the book, I switched to ML in the chapters that have predictors, because I wanted to be able to do some kind of omnibus multivariate comparison. I wasn't as good at these back then. So that's one of the things that I'm going to switch probably is to do it this way instead, so that I can stay in REML in the second edition. So watch out for that. In R, by the way, folks, certain commands, like I think ANOVA does this, I've seen it happen, it will switch, it will re-estimate your model in ML if it catches you doing this. And so, like, it's trying to help you, but then you're not talking about the same model, which is kind of disconcerting. Degrees of freedom, Palooza. So you've heard me say the word Satterthwaite a couple of times this semester. I use that one because it is the most common across all the different packages, and when I'm teaching workshops, usually people tell me which package they want me to focus on, and then I don't have to worry about my results being too different across different versions of the same examples. So if you're testing one thing with denominator degrees of freedom, you get a T. If it's no denominator degrees of freedom, you get a Z. This happens by default in state of mixed. You have to override it with the df command. This is also the case if you're in generalized models, so for multi-level or single-level models. If you're testing more than one slope at the same time, the analog to Z is chi-square, and in fact Z squared is chi-square if you're testing one slope. The analog to T is F, and T squared is F if you're testing one slope. And then for denominator degrees of freedom, there are multiple choices. So I wanted to just briefly describe each of those. This is in chapter 5, maybe, of my book. It's somewhere in there. I don't know where. I can't remember. That chapter I nearly killed me, so I sort of have like PTSD in thinking about it. Oh, and yeah, Jonathan helped quite a bit. He helped me sit down in Fortran and like program REML one time. And that was the point at which I sort of kind of got it, because I could actually see the math work through. So in other options that you will see for how denominator degrees of freedom are computed, so in single level models, this is not a concern. Like, it's the number of people minus the number of fixed effects, the end. Well, in these models, we have to think about what is the number of. Is it a level 1 number of? Is it a level 2 number of? And then how do those get used differently as a function of how much variance is at each level in these predictors? So it's a lot more complicated. So total degrees of freedom comes from the total number of observations. So like the number of rows in your data set is T here. So under this method, level 2 is based on the level 2 sample size, so number of people minus the number of level 2 fixed effects, and level 1 is the total minus what you already spent at level 2, and then minus what you're spending at level 1. And under this method, any level 1 effect that has a random slope still gets level 1 degrees of freedom. That is not the case in Satterthwaite. So this is, I believe, the default and only choice in SPSS last I looked. You can add it to all of these things that we've been using. This is a dude's name, of course. Satterthwaite was like 1946 or something is when this methodology came out. It was originally developed as for use with a 2-group t-test, given unequal residual variances and unequal group sizes, and so they essentially hacked that machinery into working in the multi-level case. So when we're using Satterthwaite, level 2 degrees of freedom will often resemble the number of people. So this one will be about the same. Level 1 is different though. So level 1 slopes will have level 1 degrees of freedom if the slope is fixed only. But if it does have a random slope, it switches to look more like level 2. And it's not exact, it's more like, but this can matter. So when you're looking at your output and you see that you have a significant fixed slope, and then you test the random slope and let's say that's significant, your fixed slope may become non-significant because it's now being tested with a different denominator degrees of freedom. You would still leave it in though, because the fixed effect is what the random effects are varying around, so they are the center of the distribution. So I just want to put that, make you aware that these things can shift across models based on what you have. There's one more that you will hear about, and this is two different people's names. Kenward Roger, or KR, or Kroger, which I think is a grocery store. Can I get a judge's ruling on that? It's a grocery store, yeah. It's the one that's red and it has like 17 different names depending on where you are in the country. In Lawrence, it was called Dillon's. I think it's called Kroger. It's also called, in Omaha, it's a different one. Baker's, I think. There's this one chain that, like, thank you, I'm not crazy, right? It's like the same font, the same logo, the same like frequent shopper value cards. Fred Meyer is another one. Okay. Yeah, I don't know why you need to rename your grocery store based on where you are, but Yonkers is the same thing, by the way.
It's all mergers.
Yeah.
Kroger's buying everything.
I guess, but Kroger, not the store. Kroger, the degrees of freedom method. So this is Satterthwaite with respect to what it does for degrees of freedom, but it actually changes your standard errors too. So this methodology is trying to better adjust for the fact that in small samples, your variances are not going to be well estimated. So it sort of inflates your standard errors a little bit to try to get back to something that is a more reasonable solution. So I don't use this one because different packages will render it just differently enough to screw up the homework system. But this is the one that is recommended in practice for small samples. How small? Small. Like real small. The literature on this is in the context of like agriculture and having like 6 plots of land and there's 3 in one kind and 3 in another kind. Like that's where this stuff matters. If you have 100 people, it's fine. And as evidence of that, critical t-value at denominator degrees of freedom 20 is 2.086. So that's the benchmark you have to pass to be significant at that sample size. But if you say, can I just pretend it's infinity? Then you only have to pass 1.960. So there's very few situations in which you would come to a different conclusion as a function of which of these degrees of freedom you're using. I told a joke in a conference once. The acronym in SAS for this is DDFM. It stands for Denominator Degrees of Freedom Method. And in my talk, I said it stood for, dude, doesn't freaking matter. Hey, I got credit for not swearing at a conference, all right? Because you know the version I was going to go for. And I gave that talk in like 2011 or something, and just last year someone brought it up to me at the conference who had remembered it. It's like, I made an impression. I'm not sure if this is a good thing or not, but I did. So I will give you one more anecdote. I once reviewed a paper where folks were talking about degrees of freedom methods and how they mattered in practice or whatever, and they had used R for everything, and they ended up in some models with more degrees of freedom than they had people. And the conclusion that they drew was, oh, Satterthwaite doesn't work because you see the numbers don't make sense. And I'm like, no, Satterthwaite did not get this wrong. Whoever wrote that R package got it wrong. So I would be careful in looking at the implementations of these things because they may not be the same across all different permutations of estimating these kinds of models. So, there, wrapping up. Did I answer your question? Like 20 minutes ago, right?
That's like the longer answer than I expected.
It is a longer answer because there's not a good answer, I would say. Like, I think it's useful to know whether something matters as a separate point of inquiry than whether it still matters after controlling for other stuff. But beyond that, I think there's room for reasonable people to disagree about how to proceed through the models. So there's the wrap up. How does multi-level modeling handle incomplete data? It don't. It deletes the rows that are incomplete. And what do time invariant predictors do? They modify the growth curves or just adjust the intercepts. They explain the level 2 random variance for the term that's in that line if it's there, and they explain residual variance in cross-level interactions if not. There. We did it. That's the last slide. I know. Yay! This isn't the last day of class though. This is just the last day of like organized content. Okay, fine. Yes, that was going to be my next thing, is to ask if there were questions before we adjourn for this garbage day. Nope, we're good? Good for now? All right, then if you haven't done so, please work on your formative assessment for Thursday so we can talk about those story problems. And I hope to see everyone then. Let us know if you need anything, okay? All right. Bye for now. Have a good garbage day, everyone.